let's look at some rules that will allow us to do our calculus even more efficiently. The first one we're going to look at is what's called the chain rule. There's the formal definition of the chain rule. So u is representing some function. So if you have some function to the power of n as opposed to just x to the power of n, we still differentiate it the same way. So we bring down that power of n, we lower it n minus 1. But what we must also do is multiply it by the derivative of whatever that function is. Okay, that's a kind of complicated way of remembering it, and that's why I don't use that. This is how I remember it. Basically, it's anarchy. Okay? All you got to remember is anarchy, because we bring down the power. That's anarchy. So bring down the power, but then we get really aggressive and we throw them on the ground. Not only have we brought them down, we're going to throw them down and put them on the ground. So after we bring down the power, we lower the power. Okay? And then finally, we want to put the boot in. Because, once they're on the floor, we just go... And we're gonna kick them so hard that their insides are gonna come spilling out. So it's anarchy. Bring down the power, lower the power, dip the inside. And that's how you remember it. Okay? Now the advantage of remembering it this way is because you do what you're thinking. Well, no violence, of course. So back to this example from yesterday where you remember yesterday I expanded the whole thing out. Reality is I probably still would expand this one out because it's quite a simple one, but let's use this rule on this one. So we bring down the power so the 2 comes to the front. We lower the power so that now becomes 1. But then we're putting the boot in. The inside going to spill out. So the derivative of what's inside those parentheses comes spilling out, and there it is, 2. Now all I've got to do is tidy that up, and there it is, 4 times 2x plus 1, which is the same answer as yesterday. Of course, yesterday we had it as 8x plus 4, but it is the same thing. The advantage of this rule then is when you've got something like this, power of 7, we don't have to expand out this whole thing to the power of 7. We can still do it the same way. Bring down the power, so 7 comes to the front. Lower the power, becomes 6. Put the boot in, out comes the derivative, and there it is, 3. So 7 3s are 21. We have our answer. Try another one. Doesn't have to be a linear function. I've got a quadratic in there. Again, bring down the power. 3 comes down. Lower the power. 3 becomes 2. Out comes the derivative, 2x. Tidy that one up. We get 6x times x squared minus 10 to the power of 2. Okay? Bring down the power, lower the power, diff the inside. Doesn't matter if there's a number out the front, just like we saw yesterday. Bring down the power, it becomes 30, 6 5s. Lower the power, 5. Diff the inside, negative 2, tidy it up. So remember it that way and you can't go wrong. I talked yesterday about this thing called implicit differentiation, which is essentially just this, chain rule. Because it's this idea. When you've got this function you're differentiating, well, instead of differentiating with respect to x in this case, I'll differentiate it with respect to t, but then times it by the t dx. Because if you have a look at your chain rule, that's what you're really doing. Remember, u is a function of x. And we say, well, instead of differentiating it with respect to x, I'm differentiating it with respect to u. But then I have to multiply by du dx, the derivative on the inside. So really, it's all the same thing. Implicit differentiation, chain rule, call it whatever you like. But do you remember when we looked at parametrics? And we said we could rewrite it as a pair of measures. So say we had a parametric form where x is equal to 4t and y is equal to 2t squared, and we wanted to differentiate that. Well, I could differentiate the x, but do it with respect to t. So I'll get dx to t is 4. And I could differentiate the y, but do it with respect to t, and I get 4t. Not 40, but 4t. Now I can combine these two together because I say, well, hang on, dy dx, that would be dy to t times the t dx. So dy to t is 4t, the t dx will turn the dx to t upside down. I get 4t times a quarter, and we get the answer t. Well, there's the answer in terms of t. If I wanted it in terms of x, I could go back to my parametric here. X is 4t, so t would be x on 4. So there would be the derivative in terms of x if I wanted to do it that way. So this idea is quite useful when you're dealing with parametric forms. Okay.